Hello, this is David Simpson with Muleshoe Engineering. Today I'm going to talk about the comparative risks of hydrostatic and pneumatic pipeline testing. Static testing. When we talk about the tests that are done on pipelines, they will include leak testing, which is typically done at pretty low pressures, a fraction of allowable pressure. Strength testing, which is typically done at a multiple of allowable pressure. When we talk about strength testing, the line is filled with a test fluid, pressure is raised to the designated pressure, and it's pretty typical to use 1.25 or 1.5 times the maximum allowable working pressure, or MAWP. Pressure is held for the designated time while recording pressure. At the end of the test period, the pressure chart is evaluated for a pass-fail assessment. Regulators and company policy have a lot of advice for selecting test fluids and rules to provide for personnel safety during the tests. When we talk about hydrostatic tests, the test fluids is typically water, sometimes with additives like a biocide, antifreeze, or corrosion inhibitor. It's the most common test by a long margin, and it's seen as low risk. Pneumatic tests. They're typically done with air, compressed air, or bulk nitrogen. They're seen as extremely high risk by many operators and regulators. Evaluating the actual risk requires an understanding of energy storage, energy conversion, and energy transportation. Let's talk about fluid energy. At any pressure and temperature, fluid at rest has internal energy. At atmospheric pressure, the fluid has the base energy. At elevated pressures, the fluid contains the difference between the energy at base conditions and the energy at elevated conditions for the entire volume, plus the total energy of the mass that was added to cause the pressure to be elevated. The amount of mass that must be added to reach a specific pressure is a function of the compression resistance of the fluid. It's a term that might not be common to most of you. Let's talk about it. In a liquid, the bulk modulus defines the pressure required to reduce the volume of a given liquid by 1%. Reasonably arbitrary amount of reduction in volume. For water, the bulk modulus is 319,000 psig, so it's a big number. You can determine how much water has to be added to reach a given pressure by this arithmetic, and it works out to your test pressure in psia times the volume of the system divided by 316,000 psig. For gas, the added volume is the real gas law. So it's test pressure times the volume of the system times the conversion to get back to standard conditions. Explosive decompression is the rapid conversion of stored energy in a fluid into kinetic energy. Rapid conversion is the important part there. Recent experiments at the University of Indiana, another one was done in Australia, a couple other places, show that an explosive decompression event can only last for about 20 to 50 milliseconds. That's 0.02 to 0.05 seconds. The fluid velocity is limited to the speed of sound, so only the mass that can learn about the failure, call it 25 milliseconds, and then move to the failure location in another 25 milliseconds, can participate in the energy conversion. Fluid farther than about 50 feet from the failure doesn't explode. It just exits and makes a lot of noise and makes a mess. But it's not an explosion. Here's a video of a hydrostatic test. Wait for it. Notice that didn't take very long. What do you have? But it was exciting.
God damn it.
Here's what we're looking at. We're looking at 3/8 inch wall thickness pipe that just peeled back. I think there's a 26-inch line, and it's standard wall. So you're seeing a lot of mass, a lot of metal mass ripped away. That's a lot of force took place in that piece of pipe. Especially when you think of the pipe is curved, so they had to overcome the resistance to bending of that curve. Let's look at a separator example. If I compare atmospheric pressure at 60 degrees to 900 pounds at 60 degrees, water internal energy goes from 28.1 BTUs per pound to 30.6. Air goes from 124 down to 118. That's just a function of the physical characteristics of the gas. So for a 30-inch inside diameter, 10-foot seam-to-seam pressure vessel with hemispherical heads, the volume of this vessel is about 53.3 cubic feet. The mass of test fluid at atmospheric pressure with air is about 4 pounds. About 3,575 pounds of water. The mass of the test fluid at test, air goes up to 272 pounds. So I have to add a lot of air. The water just goes up a tiny bit. So the energy that I've added for the air, I've added almost 32,000 BTUs. For the water, I've added 9.2 thousand BTUs. If I convert those BTUs into an equivalent amount of TNT, then the air test would be about 4 pounds of dynamite, 4 pounds of TNT, and the water would be about 1.2 pounds of TNT. So there's a fair bit more force in the separator test with air. All of the fluid is within 50 feet of the failure, so all of it participates in the explosion. But what about a pipeline? Well, for a 30-inch ID, 1-mile pipeline tested at 900 pounds, the mass of test fluid at atmospheric pressure, air's got nearly 2,000 pounds, water's got 1.6 million. The mass of the test fluid at test, the air goes up to 123,000, and the water's slightly over the 1.6 million too that it was. So the energy that I've added 14 million BTUs of energy. That's about the amount of natural gas that a person uses in a year. For the water, I've added 4.2 million BTUs, which is about the amount of electricity that a home uses in a month. So the TNT equivalent of the entire fluid, 1,300 pounds of TNT for the air test. That's a scary number. 565 pounds of TNT for the water test. Still a pretty big number. But wait, not all the energy can get to the failure. Only the amount that's within 50 feet of the failure. So the energy that can participate in an explosive decompression is 59 pounds of TNT for the air and 565 pounds of water, which didn't change. What if the line was 5 miles long instead of 1 mile? The energy that can participate is still 59 pounds of TNT for the air, because that's all the mass that can get to the failure in 50 milliseconds. But the water goes from 565 pounds of TNT to 2,850 pounds of TNT. 2,850 pounds of TNT. In the 5-mile case, 2,700 gallons of water would be ejected. That's 37 feet of pipe in either direction from the failure, so it would all be ejected. Here's some examples of various tests using the standard pressures for a class 1500 test or 900 or 600. We do a lot of class 300 stuff in the San Juan Basin. So if I do a class 300 test with air and it's 50 feet long, then I have a definite preference for using water. I got a lot more energy in the gas, in the air, than I do in the water. But if I go out to 500 feet, then I start making a different decision. So if I've got a piece of pipe longer than about 500 feet, then the air is going to be a lot lower energy than the water if it fails. And it's the same for all of the various classes. You know, if I'm doing a class 1500 test, I've got a lot of pressure. That's a 2,400 pound test. And if it fails, if it's longer than 400 feet, I'm going to get a lot bigger mess with water than I am with air. The concern about the risk of pneumatic tests comes from two sources. Tests of vessels in shops. A hydrostatic test failure puts water on the floor. Kind of messy, no big deal. A pneumatic test failure puts shrapnel through the wall. That's a big deal. The other source of concern is from a document that has come to be known as the NASA Glenn Research Methodology. It was developed at the John Glenn Research Center. A summer intern calculated the stored energy in the gas during a static test. This methodology has been used successfully for vessels, and it works pretty well for vessels. Then the summer intern, without supervision, converted the entire stored energy to an equivalent mass of TNT at a single point. This is a big number, if the line has any length at all. This report is no longer available on the NASA site or any place else I've been able to find on the web. It seems to be possible to actually delete a document from the internet, although it can't have been easy. Many companies and regulators adopted this methodology before the document was rescinded by NASA. NASA made a big deal about publishing the document, not such a big deal about removing it. There's a reason this report is no longer available online. It is utter nonsense. There's also a good reason that regulators and companies accepted it. It was published under the NASA letterhead, for goodness sake. Because of this incompetent document, many companies prohibit pneumatic testing altogether. Many other companies require excessive exclusion zones during a pneumatic test. And an increasing number of regulators are prohibiting pneumatic testing, or they're setting exclusion zones that are sometimes miles across. So if you're going to do a hydrostatic test, there's things you need to be thinking about. Every fluid has mass. An empty 12-inch standard wall coated steel pipe weighs 50 pounds per foot. If that line is full of gas at 1,000 pounds, that 12-inch pipe now weighs 53.6 pounds per foot. A little bit heavier, but not a lot. Normally, people will use a design factor of 2, which would rate the pipe stands at 106.4 pounds per foot. 200 foot of pipe full of gas weighs 10,726 pounds. The pipe rack would typically be rated at about 21,280. If the pipe was full of water, it would weigh right at 20,000 pounds. How far do you trust the design factor? Did they really use a factor of 2? Or did they fudge it? You're awful close with a pipe full of water. So you want to be careful of hydrostatic tests of gas lines on pipe racks because you never know what real safety factors were used in the design. When you stack the mass of a fluid vertically, the mass on the top applies pressure to the volume on the bottom. For a water-filled line, every 1 foot increase in elevation adds 0.433 psi to the bottom. For gas, the added pressure is a lot smaller. I mean, in the atmosphere, 55,000 feet of atmosphere adds 14.7 psi. So it's not very much. If we look at this example, we've got a point A down here at about 5,100 feet, a point B up here at 6,300, and a point C out here at about 5,800 feet. So I want to do a 900-pound test on this line. Where do I put my test gauge? Well, if I put it down here, then that means I'm not going to test the pipe at the top. Now I'm going to go to 900 pounds here, and I'm going to be at 341 pounds up here and about 500 here. Not much. So if I set it here, now I'm at 1,400 pounds down here, and that's way over what I want to test at. And I'm at 1,100 pounds here, so that's not a great place. So if I set it down here at point C, then I'm only going to test this up here to a little bit over 600 pounds. And I'm going to test this down here to 1,200 pounds. So really there's no good answer to how to test this line with hydrostatic. I mean, you could install a valve here somewhere, maybe right here. Be hard to get a welding truck up to that, but you might be able to. But then how are you going to operate it? That would really end up being a bad answer. All water will have dissolved gases that have to be allowed to leave before the test can begin, or you get funny test results. If you don't degas the water in your test, you will almost never get a successful test. Every drop of water from any source is going to have microbes in it. I've never tried to grow microbes in any water sample that there wasn't microbes to grow. Any water left behind at the end of the test has a high potential for initiating microbiologically influenced corrosion, or MIC, even before the line is actually placed in service. We normally dry the lines using foam pigs pushed by compressed air. We have to usually run pigs 3 to 10 times to get a line acceptably dry. And often at 10 times we're still getting quite a bit of water. We're going to leave water behind. Some water sources are going to be corrosive. Biocides and corrosion inhibitors are never better than 60% efficient. At the end of the test, what do you do with the test fluid? Well, hydrotest water is an industrial waste because it picked up oil and grease and corrosion products from inside the pipe. So your water disposal is expensive. It's now an industrial waste, not an oil and gas waste. So I can't go to an oil and gas disposal well with it. I have to take it to an industrial water disposal. How much water are you going to need for your test? You got to remember when you're ordering water that 80-barrel trucks never hold 80 barrels. Never yet. The water requirement in barrels per 1,000 feet equals the pipe ID in inches squared. So if I've got a 10-inch pipe, then I'm going to need 100 barrels of water for every 1,000 feet. The source of liquid and liquid quality, if I'm using river water, pond water, or produced water, I have to treat it for microbes. There is just too many nasty things in that water. I want to verify that the train's going to allow a test at all. You got a 1,000-foot hill, you could bust the pipe at the bottom without really trying. Verify that the pipe supports for above ground piping is going to bear the weight of the pipe full of water. Select a monitoring point, a fill point, and a vent point. Define a water degasification period and pressure. Determine the water disposal method and ensure that it complies with the federal and state regulations. And the regulations get more difficult every year. Pneumatic tests are similar for air, inert gas, or natural gas. And let me talk about the 300-pound gorilla in the room first. This is a famous test in Shanghai, China. This vessel, here's the rest of it, wasn't part of the test. They were testing against a shut valve, which is a pretty sketchy undertaking in the first place. But that's what they chose to do. This vessel pressured up to just a few pounds and put an up force on this top part of the vessel big enough to launch it up in the air, have it come down head first, top first. So it probably went a ways in the air. But this is not a pneumatic test failure. This is a horribly designed pneumatic test that failed uninvolved equipment. So I can do a test with air, inert gas, or natural gas. For natural gas tests, ASME B318 requires hoop stress to be less than 30% of specified minimum yield strength, or SMYS. For other gases, hoop stress should be less than 80% of SMYS. For any pneumatic test, you want to verify that the location class and the applied stresses are compatible. You want to calculate the required gas volume. Select a source of a type of gas and a gas source. You're going to bring in an air compressor, you're going to bring gas off of another natural gas line, or you're going to bring in bulk nitrogen. You want to select an injection, vent, and monitoring point. And you want to define some soak periods at increasing stress levels and set limits on approach distance at each soak point. Temperature is a big deal. At the ductile to brittle transition temperature, or DBTT, the steel pipe changes from plastic, like this. This is called a bird's mouth failure, because this somehow to somebody looks like a bird's mouth being open. But notice that all the metal is still there. It was a ductile failure. The pipe tore instead of bursting. At the DBTT, the steel changes from plastic to glass. Notice that there's a big chunk of steel missing. And you can be certain that this big chunk of steel left at a very high velocity. So that's quite the cannonball flying across the field. Basically, at this point, at the ductile to brittle transition temperature, the steel pipe changes from ripping to exploding. You never want to do a test anywhere close to the ductile to brittle transition temperature. I'll send a crew home with pay before I'll start a test below 50 degrees Fahrenheit. And this DBTT is really dependent on the metallurgy. Milder steels have a lower DBTT than higher grade steels. So if you're using an X60, an X80, X90 grade pipe, then you really want to pay attention to this DBTT because it's going to be high. For mild steel, that temperature is usually around 0 Fahrenheit. When you're executing any static test, you want to think about the rate of pressurization. What's safe? If I'm pressurizing too fast, I can prevent metal stresses from equilibrating and can fail a pipe that wouldn't have otherwise failed. Test duration. In many operations jurisdictions, the test duration is defined. A company will say all tests have to be for 24 hours. A jurisdiction will say all tests have to be at least 5 minutes. If it's not defined elsewhere, then the ASME B318, which is the gas code, calls for 2 hours. You need to define success. Some change in pressure during a test is inevitable, and you need to state the minimum acceptable pressure at the monitor station. Some people allow the introduction of more test fluid to make up for temperature change, and I don't do that. I find that way too imprecise. I don't know if I add a little bit of water, if what I added was a little bit of water or a lot of water. So basically what I say is the operator can drain fluid out if pressure is increasing, but they can't add fluid if pressure is decreasing. So when I say that, I have to say, how low can it go before the test fails? My criteria is usually if the test finishes with a pressure above the maximum allowable working pressure, then it's a successful test. So if I've got a system with a 600-pound MAWP and a 900-pound test, I can lose 300 pounds to temperature and still pass the test. Then you got to talk about test media removal. For any test, you have to specify the technique and rate of removal of the test media. Air is just air, but it can get really cold during a blowdown. So there have been a number of reported cases of somebody just opening a 2-inch blowdown and walking away from it, and sometime during the blowdown, the metal in the boss where the vent comes out of the pipe fell below the ductile to brittle transition temperature and failed brittly, and you have to start the test all over again. You have to cut the pipe out, and it's a much bigger deal than you ever want to deal with. Water's an industrial waste. It has to be treated properly. Here's a flow chart. If I start down here, then the first question I want to ask is what equipment is under test. If it's a pressure vessel, I'm going to do a hydro. I don't need to go any farther. But if it's a flow line, then if I'm expecting it to be a liquid, I go over here and say, do I have any issues with getting rid of the water? If not, then do I have any corrosion concerns? If not, then I'm going to do a hydro. But if my expected product is gas, then if it's more than 500 feet long, I'm not going to check anything else. I'm just going to do a pneumatic test. If there are above ground supports, I'm going to go to a pneumatic test. If my change in elevation over the length of the line is more than 250 feet, then I'm going to a pneumatic test. If I have water disposal issues, I'm going to a pneumatic. If I have corrosion control concerns, I'm going to a pneumatic. Working with pressurized fluids has risks. I want to avoid the risks that I can. And for example, I want to place the test gauge as low as practical during the hydrostatic test. I want to minimize the risks that I can avoid. For example, specify a minimum ejection temperature considerably above the ductile to brittle transition temperature when testing with bulk nitrogen. Bulk nitrogen is cold. It is really, really cold. And if I don't specify a minimum injection temperature, they can inject it at negative degrees, minus 20, minus 30 degrees, which is definitely below the ductile to brittle transition temperature. And a large number of the failures that have happened with nitrogen testing have been because the engineer didn't specify a minimum injection temperature. You want to understand the regulatory and company policy constraints. Don't allow an unreasoned fear and superstition to push you towards suboptimum fluid choice. You want to design the test and ensure the test is performed according to your procedure. Too many engineers spend a lot of time specifying valves by model number and specifying grades of pipe and mill runs and mill specs and on and on and on. And then at the end of all this specifying, they say, and test to 900 pounds for 2 hours. Leave everything to the field to make all the decisions, and you get what you deserve. I want to thank you all for your attention. Additional information can be found at my website, www.muleshoe-eng.com. My email address and phone number are here. This presentation is going to be placed on this Mule Shoe Engineering webpage under samples in case you want to play it for somebody else. Thank you very much for your attention.